Hey everyone, welcome back for lesson 4 in our AP Calculus course. Today's lesson is about the squeeze theorem, also called the sandwich theorem. I think the sandwich theorem is kind of a fun name, but I usually call it the squeeze theorem. So the two special limits that we learned and memorized yesterday can actually be proved using the squeeze theorem. Now I'm not going to go through that proof here, but I will let it be available to you. There's also several cool proofs available on the internet, but I will have the proof written out for you at the back. And actually, this brings up several points. When I teach calculus, I do not go into formal theorem proofing too much. Because I feel like you don't have as firm a grasp on it yet. Instead, let's just use the theorems, understand the theorems, and then in time, you can go back and prove it and really see the beautiful logical structure of calculus. But it is an important theorem to know, and we will be expected to use it. So let's learn it. All right, the squeeze theorem says that if I have two functions that on some open interval containing the point C, that h is always less than g and f is in between them, then we can say that if the limit of h and g are both the same value, then f has to be as well. So let me draw a picture of that first. So I have an example problem here. Let me get rid of that actually. Let me draw a picture. So I've got a graph here. And let's say I had, I don't know, maybe like I wanted to be blue. Hold on. Let's say I had something like an x squared graph, okay? And I also had something like, I don't know, maybe like a cosine or like a sine graph flipped over, or you know what I'll do? I'll do a negative absolute value graph. How's that sound? All right, so you see how this blue function is above the red function everywhere except for at this one little point here. And I'm calling C this middle point here. So now imagine I have some other function that's always in between them. Okay? Always. Now I don't know exactly what it's doing. Okay? Now if I could just straight up evaluate this function at 0 and it was nicely behaved, I wouldn't need the squeeze theorem. But let's say for some reason this value here is undefined. Okay? But for all values that are close to it, or in some open interval around it. So technically I have to describe some open interval. It could be negative infinity to infinity, but some open interval where this situation is true. Well, then because this green function is always in between the blue and the red, even though we don't know what's happening right here, it has to have a limit that's the same value. All right, so that being said, let's jump right to a practice problem and apply it. Okay. If 2 is less than or equal to f of x, which is less than or equal to x squared plus 2 for all x, we're going to find the limit as x approaches 0 of f of x, and we'll sketch a graph to help us do that. Okay, so, let's sketch the graph of 2. Okay. So this is a horizontal line at 2. All right, now let's graph x squared plus 2. Okay, now I don't have any information about f, but I know that f is located in between these two everywhere. So I don't have the equation for f. I don't know exactly what happens there, but I know it has to stay in between these blue and the red lines. Then we can apply the squeeze theorem. But this is a good theorem for us to start with. I think it's a good theorem for picturing. It makes sense. You could see why they call it the sandwich theorem. It's kind of the two other outer functions are the bread. and the sandwich meat is what we're finding the limit of. But we need to practice using theorems properly. We're not going to be super formal about proving theorems, but we are going to be formal about using them. So here's the first thing I'm going to say. 2 is less than or equal to f of x, which is less than or equal to x squared plus 2 for, we'll use interval notation, negative infinity to infinity. Okay? Because it told me that. All right. The limit as x approaches 0 of 2. The limit of a constant is just the constant. The limit as x approaches 0 of x squared plus 2 is also 2. And these 3 dots mean therefore. And you can say either one, but I'll say by the Squeeze Theorem, the limit as x approaches 0 of f of x must equal 2. Now, you could probably get away with not saying that very first line since it was so explicitly stated right here in the problem. But if you're making any kind of inference about that, you need to be clear. And so it's better safe than sorry to just go ahead and state it usually. But let's make sure that we got all the parts of the Squeeze theorem. So let me pull this up. So we have to have that this relationship of the function in between the other two for all x in an open interval. Well, this is an open interval. See the parentheses? Except possibly at c itself. We have to show that the limit as x approaches that value of the bottom function and the top function both have to be the same value. Okay, and we showed that they're both the same value of 2. Then we can conclude it. And what do we do when we conclude? We cite the theorem. Practice using and citing theorems properly. This is a huge part of your AP Calculus class. All right, I've got a practice problem for you to do. Please practice using the theorem appropriately. All right, pause the video at this time. Do your best, take your time, and when you're ready, unpause it and we'll go over it. Okay, welcome back. Let's go ahead and graph in a graphing calculator. So that's nice that we get to use that. So I got y equals the absolute value of x, and I've got y equals negative the absolute value of x. And I'm going to graph x times sine of 1 over x. And let's take a look at that. Well, I definitely don't know what's happening right here at the middle. In fact, I could zoom in and in and in and in and in, and you'll see that this gets more and more erratic in there. But it's always bounded between there. Now, to really do this well, we should prove that the absolute value of x, negative the absolute value of x, is always sandwiching x times sine of 1 over x. And I didn't ask you to go that rigorous, but we certainly could explain that. So let's take a second and do that. X times the sine of 1 over x is less than or equal to the absolute value of x and is greater than or equal to the absolute value of x for all x except which one? Except 0, because you can't divide by 0. But that's okay, because that's the value that we're using. As long as the only time it's not that way is that one value, we can use the squeeze theorem. So how will we justify this? And the way you would do that is you would explain that the sign of 1 over x has a range of -1 to 1. So what we are doing is multiplying x by a value as big as +1 and as small as -1, and everything in between it. And so that's why it would have to be in between these two functions. And so some sort of logical steps like that would be what you do. But we're not going to do that right now. We're just going to make the statement, and that's pretty much the way it works for these things here. As long as you just make the statement, you don't have to go too in depth with how it happened. All right. So we know that. Now we got to find the limit as x approaches 0 of the absolute value of x. Well, that is clearly 0. You can see that in the graph. And the limit as x approaches 0 of negative the absolute value of x is also 0. So I'm going to conclude by the squeeze theorem that the limit as x approaches 0 of x sine of 1 over x must equal 0. And while we're at it, make sure you're not doing anything silly like saying, by the squeeze theorem, it's 0. Please do not use pronouns. What is 0? Be very explicit in your work. It's time to practice writing like a mathematician. Good luck on your assignment, and I will see you again for the next lesson.